Afternoon. My name is Gerald Albertini. I'm an application engineer for MathWorks, and I'm based in the French office in Paris. And today we're gonna go through an introduction of the new features for wireless. We will cover a kind of a wide range of applications. But before we start, we just would like to know a little bit of background about you, where you come from, which kind of industry, so that we can adjust our future presentation and make sure that we can target our presentations correctly. So I guess we've got a quick poll. Seren, maybe you can start the poll, and then we'll be able to get started. Okay, so and this is the only question we will ask today. I mean, the only poll, just so that we can better understand your background and make sure we provide focused information. Okay, so let me get started. Okay, so we're going to focus on wireless communication today. And of course, whether you are in the automotive industry, aerospace, defense, electronics, software, wireless communications become widely spread, and they are everywhere. So it goes from the very low level semiconductor components, baseband, RF antenna, so the building blocks. We are working a lot with users building communication infrastructure. We'll talk a little bit about 5G. We'll talk about WLAN. We'll talk about Bluetooth. So we'll see how MATLAB and Simulink can be used in these environments. Of course, we talk about user equipment, mobile devices, and they can be in very wide range of applications, going from mobile phones, which is probably the most widely known, but also tactical radios and additional and emerging applications for communication. And of course, we will not address all of those, but communication is everywhere in the automotive industry, more and more with vehicle to vehicle or vehicle to anything kind of communication. We hear a lot about smart home, smart city, about new usage of communication in the medical environment, especially with the new capabilities of 5G. So really widespread. And so that's where it may sometimes be a bit challenging, because we need to address the complete system for very different applications. And of course, constraints and requirements may be very, very different. So let's see. So what we're going to cover today, we're going to try to cover three big kind of topics. We'll talk about this first part here, which is the mobile and connectivity standards. I was mentioning 5G, WLAN, Bluetooth, LTE. So we'll see that we introduced recently a new toolbox, which is called Bluetooth Toolbox, and I will give you a quick overview of this toolbox. In this case here, the goal for us is to provide tools, toolboxes, functions, examples, reference applications that are fully compatible with the standards, because the standards are becoming more and more complex. When we look at the 3G to 4G to 5G, the complexity is always increasing. The standards contain more and more pages, more and more references that we've got to check. So this is something we are really focusing on, and these products have been very successful so far. We'll also talk about, and I will try to introduce the system level modeling. And what we want to provide is a unified design and simulation environment. Again, designing a complete system, designing a communication system require very different kind of skills and different kind of people. People focusing on the baseband, on the file layer, on the algorithms. Other engineers focusing on the RF with all its funny behavior. And this is becoming probably even more and more challenging because of the millimeter waves and the beamforming that is required at these frequencies. We also have to integrate everything with antenna, MIMO system, massive MIMO system, beamforming, beam steering, all these kind of things that require a phased array. And then, of course, if we want to model the whole thing before going to production, we also want to make sure that whatever the choices we've made here will allow the system to be operational in different channels and propagation conditions. If we are talking about satellite communication, challenges may be different than talking about a 5G backhaul communication operating in millimeter waves. So we really want to provide a complete set of tools to build a complete system model, a complete system simulation. So I will briefly talk about those. So these are the names of the products that apply here. And of course, we've got the antenna, the phased array, the RF modeling. And the thing here, the only point I want to stress is that it's designed to work all together. That's one of the big things. And then we've got the last pillar we are trying to address, which is the prototyping and testing. Simulation, building a simulation, it may be complex, but it's still relatively simple compared to the real world, because in simulation I can ignore some issues that happen in the real life, synchronization, phase shift, frequency offset, and all these kind of things. But as soon as we go on the real hardware, we will have to deal with all these problems. And so here, our goal is to be able to provide tools that will allow you to easily connect to instrumentation or software-defined radios so that you can validate your algorithm, validate the system, make some RF measurements, make sure that it complies with standards and so on and so forth. But also be able to deploy the code on a specific target. And we'll talk about software-defined radio at the end of this presentation, and I will try to show you the new tools that we've been introducing. We've got this DSP-HGL toolbox, which is new, this wireless test bench, which is also a new product focused for the labs, and wireless HGL toolbox that some of you may already know that allow you to generate VHDL code that will run on an FPGA, and so go from your model directly to your actual equipment. So this is one of our goals, is really to start with very high level functions so that you can put together the system, include all the impairments, include all the RF, include the antenna and MIMO, model the channel, but also be able to test on the actual hardware and even generate code that will run on actual hardware. And here in my first part, I will stop after each part. I've got a few chapters to go through to ask questions. Of course, if you've got questions, please do not hesitate to ask in the chat or just to ask to unmute and ask the question. I will stop at in a few minutes so that we can review what has been discussed. So as you may know, if you look into MATLAB, there are more than 100 toolboxes today that address a very wide range of applications. And here among the new products that I wanted to mention, So we've got some new products, which is this deep learning HDL toolbox that I will mention at the end, that allows you to take deep learning algorithm and port directly onto an FPGA. So this is something we've been investing a lot into. There is a big trend, which is autonomous system. And I'm just mentioning autonomous system because communication is part of this autonomous system. You need to be able to control, to update, to get information. So we've got this new UAV toolbox. I've got toolbox dedicated to navigation, sensor fusion, and tracking. So mostly for radar. But this is a big trend I wanted to mention. The other topics we are really investing heavily into is code generation and VHDL code generation as well. So I mentioned this DSP HDL toolbox, wireless HDL toolbox. These are relatively new products. I call this topic new products, and wireless HDL was introduced in 2017. It was called LTE HDL toolbox at the time. We have renamed because we provide LTE, 5G, OFDM reference applications and blocks that then can be reused more largely than just LTE. Additional tools for RF, new tools for signal processing, a new kind of domain we have been investing is systems engineering, because of course at the first stages we are working with systems engineer, and they need to build a complete view of the system so that they can share the workload among different teams, and that's something we want to facilitate, being able to get the teams to work together in one unified environment. So we've got this system composer, which is a new tool that allows users to have a system view, and also requirements toolbox, because of course you want to track requirements that may change. You want to be able to make sure that all the requirements are covered when you're testing your equipment and so on and so forth. So all these topics addressed as well. And what I will be focusing on this afternoon will be wireless communication. So WLAN toolbox has been introduced in 2015. It keeps on evolving because the standards are still evolving. 802.11ax has been introduced. 802.11be is in the process, and we've got the first examples that we are providing in wireless LAN toolbox. So these toolboxes keep on evolving. I will go a little bit more in depth with satellite communication toolbox that has been introduced last year to address the needs for satellite communication, but also satellite navigation with GPS at the moment, and these two new toolboxes, wireless test bench, Bluetooth. And before I really dig into the wireless features, I just wanted to review a few new features in MATLAB, because I've been visiting a few users recently. We can now visit customers again, so it's very after 2 years spent at home, it's really interesting. And what I noticed is that there were still new features that were not really well known. So just a few trends in MATLAB, and here again it's just a small pick of all the new features that are available. So one of the trends is to program without coding. One of the goal in MATLAB is really to make sure that we can help you go as quickly as possible, provide an environment that will enable you to be more productive. And so we have been introducing the live script, which looks like this, where we can have code, we can have text, we can have the results that are updated on the fly. So this is called a live script. And one of the features of this live script is the ability to make some interactive modifications and update the code immediately. So this is, you know, small things, but that can save sometimes. And of course, we decided to go a little bit further than that. We've got different type of users. Some of our users are using MATLAB every day. They know the functions, they know where to find the documentation. You know, they are really heavy users, and they've got the function names in mind and so on. And we've got a few users that use MATLAB at the beginning of a project, or, you know, more sporadically. And the feedback they provided was that, yeah, I know there are lots of functions, but every time I get back to a project, I need to look at the documentation, the examples, and so on. And so what we've been trying to do is to provide what we call the live task, which look like this, and I will show you that in one moment, where you can interactively apply functions, algorithm to data and see the results immediately. So more interactivity. And once you are happy with what you see, with the settings you've been adjusting, you can generate the code for this. So just a few functions to save time. So for instance, here, of course, data pre-processing is one of the big things. Let's pretend you've been acquiring data and you've got some missing data that you want to clean up. You know, sometimes the data may be missing. And so here, as you can see, you can adjust the settings. The graph will update automatically. You can visualize the control and code. And so below here, you've got the code that has been generated for you. So here again, nothing very difficult if you want to write it by hand, but just ways to save you time. You can interactively adjust, see if you've got, you know, the right settings, see if the graph looks okay, and then get the code automatically. So this kind of no code, low code kind of approach is something we are looking into. And we've been introducing new live tasks. This is relatively new in 21B, and we keep on adding new features. So for instance, if I just switch briefly in MATLAB, so we can make this a little bit more interactive. So this is just my command window. I can create a new live script. So it's going to open an empty script. Here, I can sorry, I missed the E. So we can add some text. We can add some controls if I wanted to give to provide a control. Let me add one, a drop down. So let's say test 1 and test 2. So we can add some interactivity directly into MATLAB. We can add graph, we can add equations. So if you know LaTeX, you can use LaTeX equations. Or if you're like me and it's been a long time since you've not been using LaTeX, you can use, you know, just this editor. So you can build, you know, you can provide information, you can copy, paste pictures and so on. And what I was talking about was this live task. So let's pretend I want to design a filter because we're going to focus on signal processing today. So you can now call this function. So I'm connected to Teams, so it's going to take slightly longer. But basically, the idea is to have a way to define the kind of filter you want, and then it will provide additional information, let you define and design your filter interactively. Again, just a little bit slow because of the connection. And so here, you know, a few features. You can specify the sample rate, and then specify the cutoff frequency of your bandpass filter. I'm going to leave it. Let's change it just to see what happens. So here the frequency response is going to be adjusted automatically. I was not entering the right level. Okay. And so this is, you know, the interactivity in action. And here you can visualize the code. So, you know, we are making our best to provide tools that will allow you to write as little code as possible. If you want to, you still can, you know, if you're familiar with these functions and you're using it on a daily basis, you know, keep using it. If you want to ramp up on a new project, a new toolbox that you're not familiar with, if you want to explore a little bit more interactively, this is something we are providing now. Okay, and just to finish with this quick introduction, we've got the same thing for, you know, plots. You know, if you want to create a new plot and you forgot the complete settings, you can do it interactively. Define the variables in X, the variables in Y, change the markers interactively, and so on and so forth. So just, you know, ease of use, make sure that things can be made really quickly. Here you can add multiple plots, multiple graphs into the same plot. So that's just what we show here, and then the code is generated automatically for you. So, and if I just go very quickly, this kind of task has been provided for optimization, for instance. If you want to, I mean, many users are using MATLAB for optimization. And here again, interactivity is really interesting because you can visualize what happens, see the results in real time or pseudo real time, can save you a little time, and it generates code. So, you know, it can help get started. Same thing for new kind of applications, just like machine learning and deep learning. I will talk a little bit about artificial intelligence applied to wireless in this session. But again, here, what we notice is that we've got a lot of engineers like me who have been trained 25 years ago. And at this time, data science was not, you know, what we were learning in engineering schools. But now, you know, we can see machine learning and deep learning spreading everywhere, and a lot of engineers have to adapt, ramp up, see what they can do with it. So here again, we provide tools, interactive tools, to help our users get started, especially those who are not coming from a data science background, and we need to see if, you know, machine learning, deep learning, reinforcement learning could help, could provide a benefit to their applications. I'm going in the wrong direction. Code generation, that's I will focus a little bit on HDL code generation, but what we are doing is what we are trying to do is to provide ways to generate code not only on CPU, not only on FPGA, but also on GPU. So depending on your application, depending on the system you want to run on, we're really trying to make a difference in the ability to deploy your code or your models directly to an embedded system or to an enterprise system. That's especially true with FPGA and embedded applications. So I will just show you a very quick example of that. Talking about code generation, this is an evolution of the number of functions that support code generation since, you know, 5 years ago. So it has doubled. This number has doubled. 5G toolbox generate code. DSP system toolbox, most of those functions generate code. Antenna toolbox, we can generate code to optimize and to accelerate some algorithms. Phase array system toolbox, same thing. So code generation is really something that is a kind of requirement now for most of our toolboxes. I will get back to that, but what we are trying to do now is to make sure that all the functions available in our toolboxes are white box. So you've got a complete access to all the MATLAB code, and we are making our best to generate code for all of these functions as well, for several reasons. You can want to generate compiled code to accelerate your algorithm because the systems become more complex, and of course simulation sometimes may take some time and you want to speed that up. So that's one option. Or sometimes you simply want to generate code that runs on the CPU, on an embedded CPU, and we want to enable this kind of workflow as well. Signal processing, one of the big trends, and I will show you one of those applications, is to provide, again, interactive applications. You've got data, you want to quickly get started without writing a line of code. So there is the Signal Analyzer app, where you can import signals, apply frequency domain transformation, time frequency domain transformation, extract part of the data, and these kind of things. So that's one of the big trend. Signal labeler. When we talk about machine learning, deep learning, in both cases, we need data, but we don't need raw data. We need data which is labeled data. So we need to know exactly what this data corresponds to. And so we've been introducing these labeler apps to automate the process of annotating, of labeling data that may be available. So this is mostly for artificial intelligence kind of workflows, and also for artificial intelligence, but not only. A new set of functions, especially with the wavelet, and this is the wavelet signal denoiser, because we can use features, joint time and frequency domain features for machine learning. And this is something that has been requested a lot by our customers. And so that's the reason why we've got more and more applications that will allow you to quickly apply algorithms, extract some features, and generate code automatically. Multifunction, so that's just to wrap up on this part. If we now get back to our topic, which is RF, we've been adding a lot of new features, and this is requested by autonomous systems that may require kind of closed loop system. So for instance, with radar, we can now model the environment, add the terrain, be able to take the propagation into account. I will get back to that, model the antenna and the RF part. So the signal processing, that's what we've been doing for more than 25 years. So this is probably what most of you may already be familiar with. But we don't stop to signal processing. We also wanted to go to data processing. So for instance, if we talk about radar, be able to get tracks to estimate the position of the target at the next step and so on. And also be able to do all the resource management and control, which is for radar systems. If you've got multiple beams, be able to run a surveillance system, and from time to time to go and track the different targets, because we know where the target is supposed to be at a specified time. So we can from time to time go and confirm that it's still there, it's still where it's supposed to be. Test and measurement. This is something I'm gonna show you live in one second. Again, I was talking about interactive applications, and I will show you the wireless waveform generator, which allows you to generate code and to generate waveform very easily. And what we have been providing is also the ability to directly download these waveforms to a signal generator or to a software-defined radio. So let me just to finish this part, go in MATLAB and show you this application. So here in the apps tab, you we'll see that the number of applications has been growing significantly. And here somewhere we should have the wireless waveform generator. Let me find it real quick. Here it is. So this is an application, so it's going to start. And what I'm going to do is define a waveform. Oh, it's opening on the wrong window, so let me drop it, pick it back here. So how does it work? Most of the application, I'm going to show you just one because we cannot cover everything in 1 hour and a half, unfortunately. So in our applications in general, you start from the top left and the workflow goes from left to right. And so here you can open a new session, reopen a session that exists. We've been providing tools to generate, custom modulation like QAM, PSK, or OFDM. But if you've got the 5G toolbox, the LTE toolbox, the WLAN toolbox, you will be able to generate signals that meet the specs immediately. So for instance, in 5G, defining a complete 5G waveform, so here I'm just selecting the downlink. There are multiple, many features, many options. So we can do that, by opening an example, writing a few lines of code. But here, what we offer is the ability to do it interactively and to update, to visualize the signal. So for instance, here we can specify the frequency band we want to use, FR1 or FR2, the channel bandwidth, the number of subframes we want to generate, filtering and so on, the subcarrier configuration. So for FR1, it's 15, 30, or 60K. The grid size, the bandwidth parts, we can add or remove bandwidth parts and so on. Synchronization burst, define, everything interactively. The PDSCH, so the shared channel, the control channel, define exactly what you want to see in these different channel and the CSI RS. So with all the options that appear, that are selectable. So here, I'm just going to get back on a simple one so I can show you efficiently what it does. So let's pretend I want to generate just a QAM. So here it's asking me which is the modulation order I want to use. Do I want to apply filtering? Yes. What is the output sample rate I want to use? Let's pretend I want to generate it 250K with an oversampling of 0.8. The roll-off factor, which is what it is, and I can generate my signal. So here it's going to generate the signal for me. So it's streaming. So we're going to see the signal here. Generating the samples. So here it's generating a large number of samples, I guess. Let me get back to the lower modulation order so that we can see a 4 QAM display. So this is something we are all familiar with. So this is the signal after it goes through the filter, and I can export the signal to the workspace, export a MATLAB script. So this is going to be a very simple one. What I can do also is to add impairments and say, okay, I want to test a receiver and I want to see what happens if I, let's say, add some phase offset. Or if I want to add some IQ imbalances. And so I can generate the signal again. And here it's gonna, so there will be a rotation and there will be the imbalances that have been modeled here. So this is a little bit rough. That's large imbalances, but just to show you exactly what happens. Okay. And so this is the first step. So you can, let me just show you. So here, that's just phase noise. I'm doing something simple because just to illustrate, but I guess everybody understands what it's all about. Here I can export MATLAB script. So it's going to create a script for me. So nothing very difficult. Again, this is pretty simple. This is probably some of you are doing that on a daily basis, but you know, you can, if you're new to MATLAB, that's something that could save you some time. And here, if you see, we've got this transmitter tab. And let's pretend I want to generate this signal. I'm happy with this signal. I would like to transmit this signal to my receiver. So what I'm using here, trying to show you, I'm using one of these small software-defined radio, which is the Pluto. I'm going to select the Pluto here, so it's connected to my USB. The reason why I've been selecting 250 kilobits per second and an overall sample rate of 8 is that it can fit on my USB 2. So here it finds my device. I can specify the center frequency I want to use. I'm going to leave the default value at 2.4 gigahertz. I can apply again, and I can press transmit. And so here we're going to see, so yeah, we need to see here, but here it's transmitting. I don't have a spectrum analyzer connected, but it works. You can trust us. So in a few clicks, you can generate signals on your devices, whether these devices are instruments like a vector signal generator from Keysight, from Rodenschwarz, from Anritsu, as far as it can talk to instrument control toolbox, or to other devices like the Pluto or the USRP devices. So that's what I wanted to show at the beginning. And of course, yeah, other new features, autonomous system UAV. We'll talk. I mean, I just wanted to mention that because this is a very large trend. And here, of course, we show a commercial UAV. We can define its trajectories. We can, you know, simulate different scenarios. We can log the data and so on. But what is important is that, you know, we could also add communication on top of that where it could be needed. Okay, so that's for the new features. Before I dig more in depth into the communication features, is there any question? Does that make sense? Is that something you were already aware of, or is that something you're discovering? I hope some of you may be discovering a few things. No question at this point. No comment. I keep on going. Okay. So don't hesitate. If you've got you can interrupt me if you've got questions or if you want to learn more about specific topics. So here I'm just gonna look into the communication vision. What is our vision? I started to mention that a little bit. We want to provide tools that allow our users to model the whole chain, a complete system. We want to provide system level modeling tool where engineers working on the digital physical layer baseband will be able to implement their algorithms using MATLAB, where RF engineers will be able to include a model of their RF, including noise, including nonlinearities, especially here we've got the PA, including the noise figure and nonlinearities of the mixers, for instance. So that can be very useful, especially when we want to, you know, make sure make a choice on the quality of the components, for instance. Model the antenna or the antenna arrays, model the propagation channel, and of course the whole thing back here. So it may involve different tools. Today I'm going to talk a lot about MATLAB. MATLAB is what we're going to find here, mostly algorithm development, defining the waveform, defining the scenarios, and so on. But we also connect easily to Simlink, which is a graphical environment, and this is going to be mostly used for the RF modeling, for everything that is physical modeling in general, so modeling electronics, modeling all these kind of impairments, and also used heavily for code generation because especially especially when we talk about FPGA, we may want to have blocks that run in parallel. Graphical approach may really speed up things when we want to deal with code generation. So we've been showing this. So very briefly, again, I'm just gonna go through an overview. If you've got specific questions, please ask, and we'll go into MATLAB and cover the topics you're interested in. But the new features we've been adding, and something we keep on working is the ability to visualize the antenna patterns and the coverage. Propagation is a key element for many of our users. You know, in simulation, if we just specify free space losses, results are always going to be very good. And when we go in the field, we're going to say, oh, it doesn't match the simulation. Yes, of course. So that's the reason why we've been introducing more features, so that we can import a terrain, so we can import a map, and with the hills and valleys, and we can apply the long rise, or we can use a Tasarım propagation model. So this is something that has been introduced in the last few years. By default, yeah, when we import terrain, we're going to use the long rise model. So it operates between 20 meg and 20 gigahertz. We will have a few elements here that you will have to specify. So we can have different scenarios based on where am I operating, what type of antenna am I using. You know, we can adjust those. We can run some kind of best case, worst case scenarios, and see exactly what could the system performances be. Well, I'm not going to spend too much time on that propagation model. So of course we've got, you know, we used to have the very basic one, the free space, and just taking into account atmospheric effect. Now we've got the long rise, and we also can connect to the Tasarım model, which is provided by Alliance Science. So this is an additional tool that you need to buy if you want to use it with MATLAB. But this is very heavily used for propagation modeling. It's a very good model. Going to the next step, when we look into 5G, we've got more and more users who are interested in millimeter waves, and they want to be able to use ray tracing to see how all their systems, what would be the propagation in a kind of environment where we will have buildings and different type of materials and so on and so forth. So this is something we can do also now. So we've got ray tracing that is available. We can define different materials and weather impairments. We can add the beam steering and see exactly, you know, and specify the number of reflections. Yep, I see your question. I will get back to the question in one moment. So visualize this type of things and get some useful information. So this is already available. I can see a question. Could you simulate transmit power from 5G base station and receive power by UE and vice versa? Yes. Yes, that's exactly this type of scenario. Here in red, this is the TX. Here in blue, this is an RX. And when we define a site, when we define a TX here, we define the antenna that is connected to it. It could be just a omni antenna or a phased array, and we can define the steering, and so the gain in a specific direction. We define the height of the antenna, and we define the power that is radiated by the antenna. So yes, and actually, let me just quickly go into MATLAB to show you a more specific example. If we go into, let me just grab it here. I'm just opening the documentation. And we've got a shipping example. I hope it's gonna answer your question. In antenna toolbox here, we've got something dedicated to RF propagation, and we've got a few examples. And here for 5G, what we've been providing was an example showing, you know, what would happen if I wanted to create a 5G fixed wireless access and take the terrain into account. Basically, let me start by the end. This is something we've been, it's not, must be a little bit higher here. This example has been defined based on this paper from Ericsson, you know, and it was in 2016. And they were describing, okay, what happens if I want to deploy 5G fixed wireless access at 28 gigahertz? What do I need to take into account? I mean, do I need a phased array, how much gain, and so on and so forth. So just to show you very briefly, we can define what we call RX site or TX site. So here we define 3 sites, 3 receive sites. And so in blue here, we're going to have the receive site. We define a TX site somewhere. It must be here. So as I said, you know, we create a TX site. The frequency is 28 gig. We specify latitude, longitude, the transmitted power, transmitter frequency, which is 28 gig. And there are additional parameters like the height of the antenna. And you see in one function, we will be able to say, okay, loss, is there a line of sight between my TX, this red thing, and the 3 RXs? If it's all green, it's fine, you've got a loss. If it's red or if it's interrupted here, we can see that something's gonna go wrong because, you know, this antenna is not high enough or this one is not high enough, but there is no line of sight in between these 2 sides. So of course we can adjust the antenna. So you see here the antenna height. We just adjust the antenna until we've got a line of sight. So very, very intuitive way of writing the code. And then after that, we refine. So then we add an 8x12 base station antenna array. And what we want to see is, okay, what does it look like? So that's what it's going to look like. And of course, I've got 3 RX sites. So I would like to create 3 beams to direct the signal to my 3 RXs. So here, first of all, I create a 3x3 RX site antenna array, which is much wider than the TX. And then what I want to do is to predict the signal strength in free space with beamforming. So here I specify the steering vector. So I just specify where the signal should be looking at. So that's what we're gonna have if I'm focusing only on one direction. And here we show how to perform simultaneous transmission. So I want to have a beam here, a beam to the second TX RX, and another beam to the third RX, and analyze what is the signal strength at the different places, TX places. And of course, then we can add some losses. There is foliage. It's the summer. It's not the spring. It's not the winter, and so on and so forth. And we can evaluate these losses. And then, of course, in the paper we are comparing with 3.5 gigahertz. So, of course, life is always much better at these frequencies. And just to show you here one function, we are using the function coverage. We define the propagation model, the gain at the RX, and so on. And we can have this type of visualization. So we've got the 3 beams going into the 3 RX direction, and we can estimate the signal level at different places based on the terrain. So I hope it answered the question. I've been making this digression, but I think it's quite interesting. And of course, if you want to have more details, more focus, please talk to the team at FİGES, and we can organize a more detailed discussion. Just to finish with the ray tracing, we started with the outdoor. Of course, our users working on WLAN or other protocols say that, but I would need to run some experiments, especially interferences, in an indoor environment. So that's also something we have initiated. There are still a few things that we are adding, but we've got the basic capabilities. We can import an STL file. So from a CAD, for instance, CAD software, we can define the surface material and the permittivity, conductivity of the environment, and we can run ray tracing using a Cartesian axis. Okay, so that was for the generic kind of communication. If there is, again, if there is any question, please, you can unmute or you can use the chat. Okay, very quickly, I don't know, let me know if that's something of interest. A satellite communication toolbox. So this is something we've been introducing last year, and there are multiple features available. First of all, we provide a link budget analysis. I would say this is the simple thing, but it's the starting point. But what we have been trying to do is to allow our users to model the orbit, so propagate the orbit for one or multiple satellites, define one or multiple ground station, and see exactly when the link will be closed, when you will have a link closure based on different scenarios. So that's something that we've been trying to make as simple as possible, and it's really very easy to use. The ability to visualize the ground tracks, of course. So that's for the kind of orbit propagation theme. And then, as usual, provide the ability to generate a waveform for satellite communication and satellite navigation system. Use channel models. So here, the one we've been introducing initially was the P618 from the ITU. And and then also provide the ability to define practical receiver. So provide all the synchronization mechanism, tracking, demodulation, decoding for the main standards. So I'm going to show you exactly which one we support. So, but basically, we provide a function for the standards, DVBS, CCSDS, interactive link budget, a few receiver design, reference receiver designs to get started, documentation and MATLAB source code and C code generation. That's what I was saying at the beginning, and this is kind of the normal thing now. That's what we go over. So yeah, what else to say? Let me just probably show you what it looks like. So here we've got a satellite. So we just use the TLE file, and what we want to see is, okay, where is it visible based on the its antenna pattern and its actual position. So being able to generate this kind of scenario easily. I guess I've got a few lines of code. What was really important is that now we've got another example where we've got a simple scenario. We've got MathWorks here in India, MathWorks in Australia, and we want to use two satellites to establish a communication between these two sites. So we define these two satellites, and we want to see exactly when they are in line of sight. So when satellite one is visible from one or the other entity, when the two satellites are in visibility with each other, and when we can transmit data. So that's the kind of tools we've been providing, just making sure, especially for the low orbit, for geostationary, it's much easier. But for the low orbit satellite, it's really very important to know exactly when will I be able to download my data, or often where should I put my ground stations if I want to get the information when I need it, and so on and so forth. And again, I will not be able to open all the examples, but very, very simple API to make this potentially complex task as easy as possible. When we talk about low orbit satellite, they are moving pretty fast, so it may generate a serious Doppler in addition to the delay that is varying. So we've been providing tools to model that efficiently. And one of the big things that have been requested was the ability to model large constellations. So now we've got Starlink, OneWeb, and all these kind of constellations. We are talking about hundreds, even now thousands of satellite, and we want to be able to model that. So we've been making sure that we were able to model large constellation, and it was operating fast. So this is one of the trends. Again, this is a tool that has been introduced in 2021, so it's just 1 year old. So now we've been adding the ability to embed an antenna pattern on the satellite itself and on the ground station, so that we can make sure that they are, looking at each other. And we will be introducing new features where we can steer the beam as well. So it's still, this is a product where there is a lot of ongoing development, many new features that will be announced over the next few releases, especially with regard to mobility. That's something we are clearly looking into. Propagation models for satellite, again, well, that's what I say, we've been modeling the P618. So that's described in the ITU. This is one of the most widely used. So that's built in. So you've got to define the different parameters, tell in which region you are operating in, and you will be able to get estimations. And just to finish with that, oops, that was a beta. I should have removed this, but I will remove it next. We've been introducing some practical receiver. So that's something that has been requested. So we've got a complete DVB-S2 receiver, taking into account all the impairments, sampling clock offset, carrier frequency offset, estimation and compensation, DC offset, IQ imbalance, phase noise. So this is something very important, because you can get started with that, make some modifications, run some tests very efficiently, and compare with your own implementation. This is very often a typical use case. Most of our users want to compare their own implementation of their transmitter receiver system with something that is in MATLAB, so that they can have an idea. I mean, they can have a golden reference, and they can compare with. Any question about satellite communication? I don't know if any of you are in this industry. But again, it's been introduced in 21. It's pretty new, and it's we invest a lot in this toolbox. It's 2 o'clock. We've got 30 minutes. Here I've got 3 topics I want to address. It's the standards, so 5G, WLAN, and Bluetooth. What I'm going to say for one is mostly valid for the others. So I will probably dig into one in details and then go a little bit faster for the others. But that's what I was mentioning initially. So we've been introducing this 5G toolbox. I showed you the wireless waveform generator, trying to make waveform generation as easy as possible. Of course, the 5G toolbox comes with a lot of examples, lots of functions that are available, but also there is a link to what we call the wireless HDL toolbox that allows you to generate code. And we've got some reference application for 5G that describe how to build a complete 5G receiver. So that's something that is really very important. 5G toolbox in MATLAB and wireless HDL toolbox to generate the code using Symlink. The use cases, they are mostly the same for the toolbox. So generating waveforms is one of the big things, especially when the standards become quite complex. I'm not going to describe the whole thing, but we can define waveforms for the downlink, the uplink, the test models, all the standard objects. So we are trying to make that as simple and efficient as possible. One of the other thing I was talking about the channel. in the 3GPP, they've been addressing this with TDL and CDL channels. So it's, there are some typical tests that you're supposed to run. So we've been implementing that as well, so that you can, as early as possible, run a test and see the results you could achieve. And so far we were really focusing on physical layer, and that's true for WLAN, that's true for 5G, that's true for many of the toolbox we've been providing. But we address more and more simulation level examples. We've been adding more features to support the Mac layer. So we are not file layer only, but we include more and more Mac layers capabilities so that you can run system level simulations. For instance, model the code channel interference between different cells, or to use, MATLAB to model a cell and see what happens for cell selection if you've got a UE that is, moving from one cell to the next and so on. So this is a trend. So we do not have a complete network level simulation tool as of now. We've got more and more examples. We are building, creating the building blocks so that we will be able to address more of this in the future. The trends, again, new features. So we are really trying to address the new use cases as they are developed and as they are defined by the 3GPP. So here, using the unlicensed modeling, which has been described in release 16. So this kind of cooperation and this kind of using 5G in unlicensed, just like WLAN, is something that is studied very heavily. And since we've got 5G and we've got 802.11, we can very efficiently now build cross-product example that use both and define some advanced scenarios. So that's also something we are paying attention to. WLAN toolbox, very similar to what I described with 5G. The use cases remain the same. Signal generation, that's the first one. Being able to build end-to-end simulation. What is my bit error rate, my packet error rate? What can I achieve the performances I'm expecting? Ability to connect to instruments, especially to make measurements, for instance, EVM measurements, or just making sure that the spectral mass test is okay. So if I've got my transmitter, I can connect it to a VSA, a vector signal analyzer, get the data in MATLAB and run some tests. Of course, some analyzer have this built in, but if you're using legacy tools or if you want to reuse existing equipment and run the whole thing in MATLAB, automate the whole thing, that's totally possible. And signal detection, so being able to provide not only simulation blocks, but also a complete and practical receiver where we really detect the start of the burst, where we synchronize the frame, where we can decode the packet. So it's something we are addressing systematically now in our new toolboxes. The standards, again, it has started, the WLAN was probably the first of the toolbox addressing a standard back in 2015 or early 16. And we were addressing this standard at the beginning, and then we at the end, the high throughput, very high throughput, high efficiency, extremely high efficiency. So AX Wi-Fi 6 is probably the most popular today, and many users have started to look into BE, and we provide the initial capabilities with BE as of today. One trend, I didn't mention that in 5G, but we've been adding some examples also, is positioning. everybody is talking about positioning these days. Bluetooth Low Energy provides some capabilities, 5G provides new capabilities, WLAN provides some capabilities. So positioning is also something we are investing in, and we've been adding examples in our toolboxes. So if I just go back in MATLAB, let me see what I can, if I can find one real quick. So here in 5G, for instance, we've got these new examples and our positioning using PRS, so the new signals that are dedicated to positioning with the description of the scenario we want to address and model, how we compute the time of arrival and how we compute the position. We infer a position from these TOAs, and a complete example. I'm not going to go through it because there is fair amount of line of code. It's 5G, and we generate the PRS and the shared channel data, so it's a fair amount of code. But we describe how to do it, and we describe reference example like this one with a description of the different techniques that are used for positioning. So that's a trend. I'm showing you this example in 5G, but we've been adding examples in WLAN and Bluetooth as well. Again, in WLAN toolbox, modeling the MAC layer and the network is something that has been requested, and we've been making a good progress on this. Especially we can know have examples like this one. So this is an 802.11ax multi-node system level simulation. So we define different APs and stations in a building environment with different floors and so on. So we've got multiple floors. We define multiple APs and STAs, and we are implementing just the EDCA this time. We generate some traffic, and what we want to analyze is the throughput at each transmitter, the packet loss, see if there are some interferences that are causing some problems with the communication. So this is something that is still evolving a lot, but in WLAN, in the WLAN toolbox, we have a fair amount of functions that can be used as of today. And the next one, I'm going to go quick. It's the Bluetooth modeling. Very much the same. I'm not going to repeat here. No, actually, in this slide, it's interesting because we've got one more thing. Bluetooth and WLAN may operate on the same frequency at 2.4 gigahertz. So coexistence and interferences is one of the use cases we've been identifying. And I was talking about localization. We also have these capabilities in Bluetooth, and we've got, we ship examples. The nice thing with Bluetooth, again, talking about network modeling, it's that network modeling is totally defined in the Bluetooth specification. So here in Bluetooth, we address the whole thing from the PHY to the network modeling. And what does it look like? So full source code, extensive documentation. I'm not going to repeat that one more time, but let me just show you something here. So generate all the variants of the Bluetooth waveforms, make some, measurements of BR, PR, so performances in different channels and so on. So what, most of our users have been doing so far. Running some standard defined tests. So Bluetooth define a specific number of tests that you want to implement. So we've been addressing those needs as well. Being able to go over the air with some, radios, such as the one I was showing, the Pluto radio. That's something we provide. And this is something I wanted to show, the Bluetooth coexistence. This is the typical use case. Several users have been requesting because they want to know in advance and see if they could make some slight modifications, propose evolutions to make things better, especially with quality of service. So that's something we've been addressing with Bluetooth, especially this adaptive frequency hopping. Make sure you can assess and see that the Bluetooth frequency hopping mechanism is going to identify that this part of the frequency is heavily used by WLAN, and it should hop outside of this. So that's a very easy way to make sure the algorithm and the scheduler you've been defining works properly. Okay, localization, I was talking about that. The nice thing with Bluetooth is that the whole layers are defined in the specification, so we've been able to implement these mesh networks. Make sure that you can have some relays and the message can go from one node to the next. We also have been adding some functions to analyze the energy consumption. This is something that is also of great interest for our users in the IoT community, because they want to operate on batteries, and minimizing the energy consumption is a big thing. So Bluetooth is probably one of the toolbox where we provide the most complete features in terms of network modeling, and we are working on that for other standards as well, because we've seen some very interesting. We've received very good feedback and interesting encouragements from our users. Okay, so in summary, very much the same as what we can do with other toolboxes. So of course, we start with the phi modeling, end-to-end simulation, coexistence, interferences. This is something here that it's true, and it's easy to illustrate in WLAN and Bluetooth because they operate on the same frequency. But all these kind of interferences is also of great interest for the satellite communication community, for our users in the military tactical communication, because they can operate in denied spectrum kind of environments. Network modeling, Bluetooth is where we've been going to the most advances, because it's all described in the standard. All the source code is available. This is the rule now. We really make sure that all the functions we provide are shipping with the source code. It's in general MATLAB object-oriented program. It's not the 3 lines of code that you could learn at the university, but it's fully documented, in general very well documented. So it's object-oriented because it's much easier to make it evolve this way. But it's all open. So if you want to understand what is done in a specific algorithm, you can open, look at the code, and if you want to get started with what we provide, you can copy paste and then make some modifications and compare if that's something of interest. Okay, any questions about the standards before I move on to the software-defined radio? Again, here, Bluetooth, WLAN, 5G, what we want to provide is, built-in functions that are compliant with the standards, so that you can focus on what you really need, your design, your verification, and not on creating or reinventing the wheel, building and testing functions to implement 5G, WLAN, or Bluetooth. So far, so good? No question? Okay, we'll have a 30 minutes session. I've kept some time at the end. The 2 next topics I wanted to address is software-defined radio. I've been showing you a very low-cost, simple software-defined radio that I'm using to generate signals. But basically, software-defined radio, I'm gonna go quick. Basically, you've got hardware, an analog front end, a transceiver. What you want to be able to do is to have an FPGA or a system on chip, so FPGA CPUs that can be used to to process the signal, and then you want to be connected to a host computer, for instance, for baseband processing. So we've got different approaches with software-defined radios, but that's also a topic where we we are investing a lot. Testing with hardware and real-life signals is critical. Again, if we stay in simulation, we can make the world perfect, ignore the noise, or just add some AWGN noise, and there are a few things that, you know, if we do not model, we will not take into account. So it's really important to be able to run some tests with actual signals. And so that's the reason why we are making our best to provide ability to connect to signal generators, spectrum analyzer, but also to software-defined radios. So low-cost software-defined radios to run, you know, very quick tests in the lab, or just, you know, do some verification, or more advanced software-defined radios to go to enable more performances in terms of accuracy, in terms of speed, and so on and so forth. In two ways of operating. So you can connect your software-defined radio to MATLAB and grab the data to MATLAB and do all the processing in MATLAB. So this is what we will call radio I/O. And the next step, of course, is to define your algorithm, generate some code, and deploy on the embedded platform. So this is what I will call targeting. And here there is a paper here from Ericsson where they provide some feedback about, you know, what they've been using, how did they use HDL coders, so generate HDL code to build their own radio test bed. So, but before that, this is a new product we have released in 22A, so 1 month ago. It's called Wireless Test Bench. I just want to give you a quick overview of this one. This is something that is addressing a need in between the radio I/O and the targeting, because building an algorithm that you want to deploy, generating code that you want to deploy on the target, it's not necessarily easy. We are trying to make it as easy as possible, but you know, you need to convert the floating point to fixed point. You need to adapt your model so that it can work on a sample per sample basis. You need to talk VHDL, you need to really understand how the hardware is made to optimize, to be able to run at the maximum speed, and so on. So, you know, it's hardware. It's not simple. And here, what we've been providing is this new tool called Wireless Test Bench. The goal is to provide a bit stream that we are going to download on the FPGA so that we can provide the maximum capabilities, but directly from MATLAB. So here, it's totally new. So we've got two main use cases: the transmit and capture wideband signals up to the full speed, and a kind of a data capture with a pre-onboard detection. And what we've been doing is we are using, right now, we are supporting only the USRP N310 and 320, which have fixed, you know, they've got a fixed sample clock that you can divide by an integer value. What we've been providing on top of that is the ability to use any sample rate, and we create the bit stream with on the FPGA so that you can resample everything and use any sample rate. So this is a very big improvement compared to what you can do with the regular kind of API. So I left the agenda. I should have removed that. Okay, just what I want to provide is feedback on the typical use case. Stream wireless signals to the host so that you can apply some data processing and run custom wireless application directly on the FPGA. So let me just go a little bit. Why did we provide that? The high data rate application is needed for high-speed transmit and capture. Wi-Fi 6, it's up to 160 megahertz of bandwidth. Wi-Fi 7 up to 320. So we had to build something to support this. But in addition to that, what we want to do is also, if we want to go to this high speed, we also want to be able to detect actual signals so that we can capture only the part of the signal that we are interested in. And we want to make sure that we're not transferring millions of samples to the host to do the processing in MATLAB. What we want to do is to make sure that we capture the right signal directly on the target and transfer only what is needed. So this is going to improve the host processing a lot. This is also something we have in mind for AI and channel modeling. We've got an input, we've got an FPGA, we've got an output, so we could very well apply some channel models. So this is future things we are thinking about. So if you've got some feedback, if you've got some if you are interested in this type of applications where there is an FPGA open to the user and you're not necessarily taking advantage of it today, or you would like to, but you know it's too difficult, it's too long, you don't have the resource and so on, let us know. This is really really something that we are currently working on. The targets we support today are limited to these USRP modules. We have been starting, we are collaborating heavily with NI so that we can support the this USRP module. So NI and ITUS, but NI bought ITUS a few years ago, so it's kind of the same company now. So this is the target we support currently. And the goal, of course, is to be able here to have up to 4x4 and here 2x2 MIMO, 200 megahertz bandwidth per channel. So that can that allows us to address the Wi-Fi 6 needs, and of course, and high resolution ADCs and DACs. So a very good dynamic range on these devices. And an FPGA that is large enough so that we can download custom bit streams that make sense. There are new products, I mean, new devices in the making, relying on the RF SOC. So that's also something we are looking into because it's going to provide extended bandwidth, much larger bandwidth in the future. So this is a new tool. And if I just go back in MATLAB just to show you what it looks like, so in the documentation, okay, signal processing, and this is the wireless test bench. And the goal, again, we build the bit stream so that we can provide examples that are very, very easy to use and that only require MATLAB. So this is a step to enable MATLAB users really take advantage of the embedded FPGA without programming it. So for instance, here we've got some capturing Wi-Fi signal based on the preamble. We know the preamble that is using trigger capture. Again, we've been providing example for WLAN because it's easy it's available almost everywhere, so it's very easy to demonstrate. But of course, you can trigger on any kind of signals. It's a digital filter. You can specify the header you're looking at and trigger on any kind of preamble detection. Again, here we remain in it's full MATLAB. There is an operation. We download the bitstream at the beginning. We interact with the running FPGA directly from MATLAB. So very easy to use. And new features that will be added over time. So here again, we can detect Wi-Fi signal here, Wi-Fi signal there. We could, define exactly how many samples we want to save or to transfer to the host, rather than transferring all this data that is not necessarily required. So improve the performances for test and measurement. And finally, looking at the time, okay, I need to wrap up. The next step is the ability to generate code and target embedded system. And as I said, it's not something simple. If you want to build a modem, if you want to build any kind of equipment from scratch, you will need to define the right RF architecture, how many mixers, what are the intermediate frequencies, and so on. You need to apply all the digital signal processing, generate the waveform, build an equalizer, build a channel estimation, and so on. You will need to define a reference design on your FPGA, and then generate the VHDL code, make sure everything fits into the FPGA and is able to perform at the right timing. And you also may need to develop drivers for the embedded system. So it's a challenging task. And what we've been doing for several years now is really to leverage our tools, which are HDL coder and embedded coder, to allow our users to target software-defined radio from their model in Simulink. And this is just an example from one of our users. Here it's BAE that has been writing this user solution. And here what they claim, they've been able to reduce software-defined radio development time by 80%. So it's significant. It's not a detail. Of course, the first time you're using, you need to learn Simulink. You need to learn how to use HDL coder. I don't say it's simple. It requires training. It requires time investment if you really want to be fully efficient. But again, we provide many tools, especially reference application I'm going to show you in one moment, that can help you get started very efficiently. So that's something we've been paying a lot of attention. So basically here, in terms of workflow, we can start with modeling the system in MATLAB and Simulink. So that's something we already can do. I was talking about radio I/O. So here we can use the software-defined radio. So this analog device, the 9361 here, represents the transceiver, the software-defined radio. So here we grab the samples from the antenna, we do the processing in MATLAB, and we can run some test verification. But of course, the next step is to say, okay, I'm happy with my processing. I want to download the processing on an FPGA, on a SoC. And still keep a link with MATLAB and Simulink, because I want to verify it's operating properly, and then deploy the complete system in a standalone. So we've got a few examples. I'm not going to show you the whole workflow. It's well documented. We've got many examples. I just don't have enough time here to go through the whole thing. But if that's a topic of interest, of course, I would be glad to run a complete demonstration or a workshop if you're interested in. What I'm going to show you, just to give you a rough idea of what is already available, is look into here, this wireless HDL toolbox. It used to be named LTE toolbox initially, and then we've been renaming it, because what we do is we initially provided examples for LTE, as its name implies, but now, of course, we provide 5G reference application. So here we've got examples that show how to run a HDL, MIB, or SIB1 recovery directly onto a platform. We explain how to deploy. We've got this NR HDL downlink receiver MATLAB reference, so that we can compare the actual receiver with a MATLAB reference. So very complete and detailed examples to get started with. So, and of course, again, documentation is very important. So we really describe how we do things. So here we've got all the processing. And then we describe the model. So here it's graphical. This is Simulink models. So it's a graphical approach. we can simulate, of course, the whole thing can be simulated. So the first step will be to provide some signals at the input that have been recorded or simulated, make sure that the algorithm work as expected. So in this case, they work because we've been providing and testing those. But we describe the whole workflow, and you can start with something that works. So you connect an antenna, you define the frequency of the nearest base station, and you're gonna be able to see the signals, to demodulate, to decode, demodulate the signals to synchronize to the base station and so on. So again, this topic in itself, HDL code generation for 5G is a complete, it's a topic by itself. We could spend 3 hours digging into the details. But what is really important here to notice is that, you know, we provide this reference application. We've got this HDL transmitter, receiver. We explain how to deploy on SOCs. So many shipping examples to help you get started and get started with code that you can you can generate code, download to the target right away, and we support the RF SoC and hardware based on the Zinc plus AD9361 devices. Analog devices provide some tools as well. I was talking about WLAN reference application. Of course, this is also something that can be used to run some tests on digital pre-distortion on DPD. This is one of a very interesting use case. Because of the advances in satellite communication toolbox, we also have been introducing DVB-S2 receiver. So here we've got a full DVB-S2 receiver. So again, starting with an existing reference application that you know is already working can make a difference in terms of time saving. There is a lot of things. I'm less familiar with all these things. System Verilog, DPI, and verification, very heavily used by people doing verification, especially in ASIC. But of course, there is co-simulation. You know, once you connect to Vivado and to the HDL code generation, code verification kind of workflow, we want to integrate with all these systems as well. I'm already 10 minutes late, so I'm gonna conclude. I'm just gonna keep on going quick here and just three minutes, just a few minutes on artificial intelligence. This is a big trend. We are hearing more and more about artificial intelligence. And of course, we've been responding to that because we've got a deep learning toolbox, we've got a machine learning toolbox. Initially, we've been putting a lot of efforts to support mostly our customers in the automotive industry, because that's where we had a big push for artificial intelligence, being able to detect other cars, pedestrians, bicycles, detect the line, follow the line, and so on. But once we've got the tools in MATLAB, we can extend it to work with other toolboxes, and that's what we've been doing. So we've been providing more and more examples to show how to use artificial intelligence with wireless and with radar. And today we hear a lot about AI for wireless and at different levels. Network simplifications, spectral efficiency, improved performances. You know, so some of our users just mentioned, I want to do the same as what I was doing before using traditional kind of signal processing, but I wanted to take less resource and consume less power. And artificial intelligence can help in some way. And the typical use case we've been addressing, so signal classification. I want to, you know, I'm monitoring the spectrum, and I want to detect different kind of modulation because it can provide some information on what type of signal is going through. Digital pre-distortion. I guess NXP has been writing an application note also on this, and show how they've been using MATLAB to develop their own DPD. Channel models and channel prediction. This is something that is available in the 5G toolbox. Beamforming. We also could use AI to improve beamforming. Wireless network optimization, many different applications. And so just in one word, what we are providing, because we've got additional tools that take care of data science, dealing with the data preparation. If we want to train a network, machine learning, deep learning, we need data and annotated data, labeled data. So we can generate data, we can clean up existing data, we can augment data, put some, more noise, less noise. I mean, well, less noise, it's difficult, but more noise, frequency rotation, these kind of things. Then we've got all the tools to create and design models, tune the models, all the hyperparameters, run some tests, and then deploy. So this is really something we've been focusing on. So I'm just going to go. So here, of course, the preparation, data preparation is very important. Garbage in, garbage out. If the data that you provide to your training, your training data is not good, the model will probably not be very good either. So just make sure that we can help providing good data. We can generate data using our toolboxes that are compliant with the standard. We can use other AI techniques like the GAN to generate data that will look like something that is already known. And then we've got all the machine learning. I'm not going to show you the whole thing, but I was mentioning the machine learning, the classification learner interactive application. So we can really explore different algorithms as quickly as possible, especially for non-specialists, for non-experts. There are a few built-in models that you can connect to directly in MATLAB. So GoogleNet, VGG, SqueezeNet. So there is also this notion of transfer learning. You start with an existing network, you just train, you disconnect a few layers, you retrain the network just to adapt to your new signal, and then you can run again. Many examples, and I'm just going to end up with this. Let me show you just in MATLAB. If you go here, I'm just going to show you very briefly, and I will conclude on this. Data science here, there is this deep learning toolbox. And in deep learning toolbox, you will find deep learning with image, time series, and deep learning applications here. And deep learning applications, you will find wireless communication using deep learning. And these are the examples we've been providing so far. So using neural network for DPD design. Spectrum sensing to identify 5G and LTE using deep learning. Using autoencoders for wireless communications. Using deep networks to detect a router or to provide some protection against impersonation, these kind of things. Modulation classification, target classification for radar, and so on and so forth. So this is growing with every single release. There are more and more examples that ship with the toolboxes that use, here in this case, 5G toolbox plus deep learning toolbox. Here we generate known signal, we go through a channel, we generate many instances, a lot of data going through different channels so that we can estimate the channel efficiently. So here again, the workflows are really well defined. We've got a lot of resource, dedicated application engineers if you really want to look into the deep learning or the artificial intelligence in more depth. And we typically work together. I mean, my colleagues from data science and myself to show how we can take advantage of artificial intelligence in MATLAB. So, but many examples. Just even if you're getting started, you want to see what has been done, how it's been done. You know, it's also very good place to get started. Okay, I'm going to conclude here because of lack of time. Now I've been that was really the examples I wanted to highlight. More and more features, more and more examples, and it's growing. Okay, my conclusion, very simple. You know, the motto of the company is to accelerate the pace of innovation, and that's really what we're trying to do. Provide system level modeling capabilities so that the team can work together, and very detailed workflows. It's that's very important. We really describe step by step. We've got a lot of webinars, lots of application notes that you can, you know, look into to get started. Being able to make the different people work together, people talking. I mean, in a software-defined radio, the team working on the antenna may not speak the same language as the team working on the embedded Linux or on the HDL. They use their jargon. They, you know, they are not. It's not the same competencies. It's not the same skills required. So we want really to make sure that everybody can work on his part, and we can put the whole thing together in one environment. And of course, what I've been showing from the beginning is really all the tools we can provide to make sure that you can reduce your time to market, because this is still critical now. More and more innovation, more and more. I mean, the cycle times are becoming shorter and shorter, so it's very important to be able to provide products quickly, efficiently. And for those who join, who want to learn more, there are more and more free tutorials or classes. I mean, these are introduction to MATLAB, introduction to machine learning. We now have an introduction to signal processing and also to communication. It's not there, it's not in this slide, but there is a communication with MATLAB on RAM. So it's free. You just need an internet browser to connect and run the whole tutorial. So I really encourage you to look into it if you've got new projects and want to see if MATLAB could help. And then, so this is these are typically 2 hours, you know, self-paced, interactive kind of class that you can take for free. And of course, then there is the complete courses that are provided by our training engineers. And here you can go in depth, and we can have, you know, focused training paths for you. And that's about all I had. I see a question, but I cannot read Turkish, unfortunately. So, oh no, Seren was writing it. So if you've got any questions, if you've got any feedback, if there is something you would like to look into in more details, we've got 10 minutes more. So please feel free. I hope you've been learning new things today. I'm going to disconnect. Thank you very much indeed. Thank you very much. Bye-bye. Have a great day.